Hello, everybody. Today we are going to talk about research methods and designs. So one of the research methods that we all know and we work with is experiment or experimental research. We try or test. Experiment means try to test, but in engineering, it's more nowadays known as analyzing a system or a process behavior under different conditions. So on the right-hand side, you see a figure, and there you have a system process. And assume that it's a black box, and we don't know what is happening inside. We give some inputs, and we get some outputs. And in this black box, in this system, we have some parameters which are controllable, or some are not controllable. Those I have shown by X up, they are controllable parameters, and Z are. For example, if your system you are working with an instrument, and you have to put the instrument in specific conditions so that it works. So that's not controllable. But the things that you give as factors to the system or parameters that you can change them, you can manipulate them and put them inside this process, then they are controllable variables. Those parameters that you have full control of them, you can change them, you can manipulate them. And the system will then the input and the output, these controllable variables, and of course they will affect the process. And also when you give the input to the system, these will influence the result, the things, the input, and what you get out of the system is an output. So this is an experiment that we have. We have some inputs, some parameters, controllable and non-controllable, and output. So experiments are used to determine which parameters has the greatest impact. So we give different parameters to our experiment to the system, and we don't know which one is stronger, which one can greatly change the result, change the output, I would say. And we need to determine which parameters are controllable, which parameters are not controllable, how suitable, to determine suitable values for X, mix means controllable variable, to minimize the output variations. Because if you change X, it is parameters inside, the output will change. What these changes, we should see this, how much these changes are controllable. Are they in random variation, random nature, or not? We try to minimize the changes at all. Suitable values for X, reducing the impact of the non-controllable variables. So if you do not have, you have some parameters that you cannot control them, then if they are influencing, you will choose X in such a way that their effects are minimized. So experimental settings should be able to realize the intended phenomena. You should do this experiment in such a way that the phenomenon that you want to investigate, you can realize it. It should be realized. It should be understandable, and you can separate interfering factors as much as possible. You have control over these factors, influencing factors, and you should simply observe the result. So these are the criteria for a good experimental setting: realize, separate, control, and observe. Keep these 4 words in mind when you do an experiment. Good laboratory practice. You should, when you do a laboratory practice, you should be very careful about accuracy of everything, measurement, the system works in good conditions, you should you should use a good plan and execute this experiment exactly based on that plan, and monitor what you achieve on the system, and you should report it. For example, when I do this some experiment, when I wrote the code and I want to check if it is working, I always have a paper and pen in front of myself, and what I get out of this out of computer, I write it down on the paper. And when I change some parameters inside that, again, I will write the result down on the paper. I will try to document it, everything with the details. So in this case, I have full control of what is happening. Some of these things that is happen, I expect to see, and some of them I do not expect. So make a journal for update for the experiment progress. So journal doesn't mean that you journal for publishing. The journal is like some papers, binded papers together, and you will write them down, what is happening, and how you have to play with this experiment to get better result. So write them on paper step by step so that you can see the whole experiment on. In this case, you have better control. So experimental study design, which design is suitable? It depends. It depends on the ability to control over and manipulate the events. If you cannot control this, then it is not an experiment, it's a quasi-experiment. Another way is randomization. Randomization means that the chance determines which element ends up in control and experimental group. Let me explain what this is. So on the left side, you see R. R is a collection of data, collection of things that I divided into parts and perform some tests before the experiment on them. So this is called pre-test. So experimental group is the things that I want to see the effect of experiment on these parameters. And control group is a group of data or group of the parameters that I do not want them to go through the experiment. And while we have wait after the experiment, I will see how much the experiment has affected them. Let me give you an example. A family has two kids, for example, two kids, and they want to go to a trip, and they keep one of them at home. They said, I usually stay at home, and they will take one of them with themselves. So the one that they keep at home is the one they control. It's a control group. It's like a control group. And the one they will take with themselves in the trip, then there is into the experiment. And after the trip, they come back and talk to the kids. And they will see about the emotions, what has happened to them. This is some simple and known example about grouping, group, control group, and experimental group. So you can simply do this if you have in your experiment different types of data, can divide it into two parts. One of them keep them constant, and one of them play with during the experiment. And after the experiment, you will look at them and test what has happened to them. So how much the experiment could influence them. That's called post-test. So it can be said that this type of experiment is quasi-experiment because you do not have full control of everything, all parameters. Factorial design is somehow when you have a system, a process, you have some inputs and you have some outputs. and you want to optimize the output. Let me give you an example. You want to, you have a company, you are creating, you are producing motorcycles. And the important is the stop, what's it called, speed of motorcycle. So it depends on different factors. For example, it can be depend on the power of the motorcycle. It depends on the wheel. It depends on the weight and the tires. Different factors, and you will try to see. You will try to play with these factors. You will give them some values, and if you play with the first one, and you see that, oh, the speed is increasing. So you keep that one, and you play with the second one, and you will just get the maximum value based on that. You see it, and when you fix for the first two, you will play with the third one. These methods of doing the experiment is called one variable at a time. So you change that. But the problem is that these factors maybe they are interacting. One of them can influence the other. So if you increase one of them, it corresponds to reducing the other one. So it means that they are interacting. In this case, we do a full or fractional factorial design. We consider all possible combinations. For example, let me annotate here. Look at this table on the right side. So I have two factors and I have one experimental value here. First, I put factor plus means the highest level, and minus means lowest level. So the highest level of X and highest level of Y, you get a value. Highest level of X, second row. Lowest level of Y, you get B. Lowest level of X and highest level of Y. And both are at low level. So this is the way that you can do a factorial design. You will do the experiment, and at the end, when you want to determine the effect of it, you will determine the effect of X, and Y, and also their interaction. And the interaction is simply you can dot X, Y. Plus plus is plus to minus minus plus minus. So you can also consider this combination for the interaction. So in this case, you can do full factorial design. It means that you will consider all interaction between parameters as well, not one variable at a time. So fractional factorial design means that if I wanted to have a design, I do not need to do this in full factorial, because full factorial design is, it depends on the number of parameters. For example, if you have 3 parameters, you need to do 8 experiments. If you have 2 parameters, you need to do 4 experiments. And if you have 5 parameters, then you have to do 32 experiments. So you see when the number of parameters increases, the number of experiments that you need to do increases as well. So which is not really, it's not really cheap, because experiments will cost, and so it takes time. So for example, for additive manufacturing, and when you want to produce some piecework with welding techniques with the 3D printers, so maybe for one piece it takes 1 day, and it costs as well. And you want to play with the factors, and you say, okay, I have 4 factors, I need to do 16 experiments. So who will give you money and the instruments so that you do 16 experiments just to do an experiment to see what is good and what is very costly? Then we try to reduce the amount of this. For example, if I reduce 1, it will be one fraction, half fraction. It will change to 2, 3, but I will still have 4 parameters, but I will do 8 experiments instead. So there are statistical methods for doing these things, doing fractional factorial design, which is related to a special course for that we have in the education. So, full or fractional factorial design is another way to see how to model behavioral process, to see what is important, what factor is important, what factor is not important, which factors are interacting with each other, which factors are not interacting. So you will get a lot of information by performing a factorial design. This is the things that those of you who are working with the experiments probably are aware of it. Required activities for an experiment. Specify what is going to be studied. Of course, you should know what you are looking for. Choice of dependent variables and choice of independent variables. So, for example, yesterday I had a discussion with a colleague who was doing some actually simulation and was trying to find some numbers fitting to some sort of experiment to get the best or highest, I would say, highest temperature for welding. So, and then we discuss, okay, which parameter, how many factors do we have in them? I said, okay, I have 3 factors. Okay, what is the maximum and minimum factor? So, okay, they have levels for them. Then we can do the design of experiment and also make a regression. So here, those 3 factors that we will give to the system and what we get out of them out of the system based on those 3 factors. Yeah, this was which we give into the system are independent variables. What we give and what we get is dependent variable. It depends on the output. I can simply say that it's the output. Dependent variable is output, independent and input. Choice of the study design. How do you design this study? How do you perform this experiment? That's another thing. Creating experimental setting, ensuring realization, separation, control, and observation. That we already discussed about these 4 things that these are for a good experimental setting. Execution of the experiment and analyzing the result and making conclusions, which are important. In a real world, you will automatically you will do these things, but we are giving you the awareness or consciousness about this here. So, systematic parameter variation is in a quasi experiment. Several variables are known to be essential. Therefore, you have to keep them fixed. But you can manipulate the rest of them so that the optimal or the desired solution that you want. This means that you play with these parameters in a systematic way. So you will look at the output. You look at the output, and you expect that this output should have this value. Then you play with these factors, these manipulated factors, to see which values that you give to these factors can help you the result to reach to that expected value. But you have to do it in a systematic way. You increase and you see that it is increasing, then you increase it again, not based on random. You put random numbers with a simulation, you use a random number generator and put them inside these variables and get output. You see, after 1,000 or millions of simulations, you will see some results. Then you can conclude all of that. That's called simulation. But Here, simulation is based on random, but systematic variation. I do it intentionally. I increase the factor because I see that this factor influence my result better, more towards the things that I want. Then I will do that. So in a systematic way, I try to manipulate the variables or the parameters, not random. So modeling and simulation. Modeling is based on the mathematical model. For example, if you want to do an experiment, you have mathematical formula, and you know that if you give this formula inside, you give these inputs, you will get the output, and you expect that your system can get this, can do the same. So you have some physics behind it. That's called modeling. Or you try to find a mathematical model for that. That's called modeling. But simulation is that you give numbers to your system or process, and you will get output, and you will do many times simulation. These random number generators, for example, you will use them and you put them, give the random numbers to the system, and you will get output. You will repeat it thousands or millions of times, so that you will come to some stable solution at the end and say, okay, this is. It's like the method for example, Monte Carlo, that for solving the system of equations. So they put different numbers inside the system until the solution of the system converges. And they find that, okay, in that way, they can estimate the values with random number generators. So it's called simulation, based on just playing with numbers. There's no physics behind. And now case study. When do we use a case study? Case study is for deepening the knowledge in a less explored phenomenon. So it doesn't mean that it is totally new. Less explored phenomenon. It means that you need some theories. You have something there, but you want to deepen the knowledge, or you want to test a theory, or check if it is more, or refining the theory. So finding the answers to why and how, or sometimes what, in the research. The case study that I have already a theory, and I know it works, and I want to see how it is work over this area, how it works over this project, how it works this organization, why these relations exist, the relation between this and that. So these are the things that we usually answer these questions by case study. A case study has, as you see on the left hand side, I have written case here, and case can be an event, can be an individual, can be an organization, work team, or a project. So it can be many things. It depends on the things that you want to study. And for any case, we have units of analysis. Units of analysis is what is going to be studied. So based on that, we have designs for the cases. Single case design is that I have one case and one unit. So I have one unit, I know what is going to be studied, and I will try to see where I can apply, where I can see that, for example, in a project with organization. Or a multi-case design, I may have more than one case. Like case studies, I can have 2 to 3 case studies, and what we have with one unit. Or I can have a case, one case study, but my purpose is to study 2 different things, or 3 or 4, but doesn't matter. One case study, but I am going to study, I have different units of analysis there, so different things that I'm studying inside that. So my goal is not only one. And also I can have different cases and different units. So before you do any case study, specify in which one of these 4 cases you are. So you have one case and one unit, or you have multiple cases or multiple units, or two cases, and based on that, you will design the case study. So say, okay, for coming to that goal, what should I do? Then you will try to write it down. Okay, I do it first this, next I will do that, third I will do that, then you will continue to the end. Single case study is good for deep understanding. Multi-case is good because you can compare. If you have two cases, for example, and you have done the same thing on both, and see that, oh, if all the results are the same or different, you can see the similarities or the differences that you would think, if the theory works equally well in both areas, or maybe in one area it works well and in the other area it doesn't work, and why? Then you should have some analytical generalization. Maybe you need to have you should add more cases to come to some generalization. So note that cases are selected on the basis of theory to replicate or add knowledge without ambition of statistical generalization. It means that when you apply the theory, your case study, even if it is the theory is known, you should create knowledge. It doesn't mean that you just apply a theory over a case and conclude the same thing that people already have taken. So what's the point then? You wanted to show that theory works, that okay, we already knew that. There's no point to show that. So if you do a case study, you need to add knowledge. You need to add knowledge. And also, you shouldn't try to do a statistical generalization. What does that mean? It means that if you have a project and you are working on that, and you conclude out of it, you cannot say that it is always like that. And for such a generalization, you need much more experiments, much more experiences, much more data. It's not, try to avoid statistical generalization. It means that from a small piece of information, you say something very general for all. So this is a little bit, it's a little bit tricky. So you shouldn't have such an ambition for case study. Case study, the focus is over the case and the units of the analysis. How do we do it? So first of all, look at research questions and see how you can have a case study that helps you to answer these research questions. Specify the purpose of the case study. Are you going to develop a theory or test your theory? What is the goal? Be clear. What are you looking for? Determine the units of analysis. Yeah, it means you should know what you are going to study. You should specify it. Perform a small pilot study. Yeah, that's the things that I want to emphasize. Let me give you an example. I had a PhD student who was going to design some survey networks. He always had the stress, oh my God, these networks are big. How can I do that? I don't know where to start, where to end. So I said, okay, don't worry. Start with 3 points. Oh, 3 points. Yeah, those were 3 points. And try to do the whole process only over these 3 points. If it works, it means that you have learned the theory. Then you can make it bigger. You can add more points, maybe up to 100 points later. But the principle of the experiment is the same. You will start from the same thing and you will go to the end. This is a small project. It's a pilot. I wanted him to do a small pilot project with 2 or 3 points, not more than that. Very few of the when he learned this, then I could make sure that he understood this. It was a pilot study that he did. When he made sure that this is working, then I can, okay, now you can generalize it. And any type of networks later that I gave him, he could optimize. So that's the thing that you can do also for yourself. If, for example, if I do my research, I want to see if my idea works. I never start a big project for that. I will try to do it as simple as possible to see if the idea or the case study works. That's what I wanted to say. Collect different types of data if possible. So, of course, the more data, more reliable results you will get. Analyze the data. We have a separate discussion about data analysis, the quality of the data, precision of the data, accuracy of data. These are the things that we have to discuss deeply later. And of course, presenting the result. There's a report, could be a paper, could be a dissertation. So this figure shows a general idea of design of a case study. You decide to do a case study. This is the first thing that you want to do. How do you decide? You will look at the research question and you will see, okay, for coming to that one, what should I do? Which cases, how do I do with the project? And then you will start with that idea. Then you go to the design. You will then, okay, now I have the case. Okay, what I'm going to study in that case. Then formulate possible propositions. Choose a case study. More about this case study. Then get prepared for data collection and pilot study. Then do this data collection and analyze it. As you see here, let me show you. Here, these arrows are two ways. It means that maybe you have to come back from the data and you will remove some data and you need to collect new data. Therefore, there is two ways here. It's not like one way. And maybe you have collected data, you concluded that this data is not suitable, but then you have to go back and prepare the data. So these are the circular, I would say. You can repeat them, go and back until the data that you want with the quality that you want, you collect them. And when you come to that, you will share the result as a report. That's the whole story of case study. Research design is another way of doing research. Activities to generate and develop a product from a need, product idea, or technology to full documentation needed to realize the product and to fulfill the perceived need for the user and other stakeholders. What is the goal of the research design? To create knowledge regarding the development process, to develop various type of support to facilitate and improve the products. That's the main goal of the research design. And research design methodology is GRM, a framework of covering entire research process. Aims to create understanding and support to improve the research design. DRM is designed to provide understanding and support to improve the research design. So DRM is one step behind the design. And after that, the research design is used to provide understanding and support to improve the product and the process development. So as you see here, from left to right. Oh my God. from left to right. DRM to design research, and from design research product and process. And DRM steps. First step, research clarification. So you need to clearly know, clarify what are you going to do. So of course you need to do a good literature analysis before. What do you do after this? You will have an initial present state, initial future state, preliminary data criteria, overall research plan. So you clarify purpose and the goal here. Next step, empirical material analysis, or step 2, descriptive study. Here, description of the present state, success criteria, and how you measure the success criteria. In this case, that you have much more understanding of the problem of the research. Step 3, prescriptive study. And here you have some assumptions and experience or synthesis. If you come to the step, you can expect from future state, support, evaluation of support, or plan for evaluation. And step 4, empirical material analysis for the evaluation of the support, evaluation of success and implication. Well, be careful that it is not necessary to carry all the steps. It depends on the type of research that you are doing. So you will have an initial, always have initial state, an initial future state, some criteria, and you have a research plan from the beginning. That's, I think, all researchers have done. Then the more you work on it, you understand better, and you change the criteria. The success criteria probably say that the one parameter that you selected as criteria, maybe you need to change it. It doesn't work. It doesn't show anything. And this success rate should be measurable, of course. And type of support that you have for this assumption and experiment. Is this research design can answer and support these assumptions that I have made or not? Let's take DRM. Action research. Action research is bridging the gap between academic research and practical. I think at our university, we all do action research actually somehow. Action research has focuses on practice, action, the work, changes, and collaboration and participation. Let me give you an example. The professor at the university has a research project, and he realized that there is a gap between academic research and practical work. So if he had some ideas, so to fill the gap, he hires a student, PhD students, and that student will work to fill that gap. So the students need to go to industry, come back, but mainly work. Everything is working inside this academia. But the research is between to fill the gap between the industry section and academic section, the theory and practice. And it has execution cycle. So you plan, you will act, observe the result, and reflect to the result. And based on that reflection, you plan again, act, observe, and reflect. So these steps are repeating. It's called execution cycle until the gap you have observed is filled up. It's called research action. And we have interactive research, which is very much popular in Nordic countries actually. And in this type of research, one person from industry and one person from academia. They work together from the beginning up to the end. So on one side, we have researcher and practitioner, can be a representative of an organization or from industrial section. And they do this joint learning. They learn together about the research. They find the problem together. They select the method together. They analyze together. They present and disseminate the result together. All the steps are together. So it's called interactive research. So what the researcher of the academic researcher is looking for is articles, books, reports, new and refined theories, develop concepts, models, and frameworks. And the practitioner from the other side of the organization is looking for usability in the organization and practicing individual result benefits for the organization, new insights, and contracts. But they are working together on this common project, the same thing, but for different purposes. Of course, there will be lots of there will be risk of some conflicts here, because these people, they have totally different backgrounds and regions in research. So, but if they can sit together and do the research, both academia and this industrial section develop together. That's very good and positive. So which research method? I have this table here. I made it with color so you can see better. It's not my table. I got it from Sapten and Gustafsson. It's like modification. If you want to do, then do a cause and effect relationship study. Experimental study is good, suitable. Case study, DRM, possible. Action and interactive, difficult. Contemporary event, suitable with all of them. Not contemporary event. Experimental and case study are possible, but DRM and action interaction, not applicable. Mature and developed area of knowledge, experimental research is suitable, but case study, DRM, and action and interaction are possible. New undeveloped area is very difficult to do experiment. Case study suitable, DRM and action possible. Possible to control impact factor. Well, experimental is difficult, and the rest are suitable. The same with intervention. So these are the type of researches that they are done. It can be done for even with qualitative data. It could be for not our industry that we do engineering, not in an engineering subject, but generally what we see at engineering science is mainly experimental and case study as far as I see. But you can apply DRM action interaction research, research as well, but not everywhere. But experimental and cases, they are very common actually in many places.